3 kilograms of cheese cost $5. At that rate, how much will 7 kilograms cost? You recognize it immediately as a problem in ratio and proportion, and you probably know a simple way to solve it. Here's how I'd do it. I'd set up an equation with two ratios. In other words, a proportion. 3 is to 5 as 7 is to what? X is the price we're trying to find, and as soon as I have the equation, I can solve it easily. I cross-multiply to remove the fractions, and then I divide by 3 to get X on its own. Which tells me that I can buy 7 kilograms of the same cheese for $11.67. That's a good way of solving this problem, finding this price for this much of this cheese, but it doesn't give me the big picture, the whole relationship between product and price. For that, we need a new way of looking at the problem, like this. What's new about it? That K, it stands for a constant. Because when we say that cost is proportional to weight, we're saying that cost equals some constant times the weight, or C equals K times W, an equation. Remember, the cost and the weight, C and W, can change. The K doesn't change. It's constant. Sometimes we say the same thing like this. Cost varies directly as weight. The words are different, but they lead us to the same constant and the same equation. Great, but how do we use the equation to solve the problem? Well, we know that the cost is $5 for 3 kilograms. So let's substitute for C and W and solve the equation that gives us to find K. K turns out to be 5/3. What does that mean? It means that we can put that 5/3 into our original formula in place of K. And suddenly we have a formula for all the prices of all the quantities of this kind of cheese. When the weight changes, the cost or price will change right along with it. But the 5/3 never changes, unless you switch to a different kind of cheese. With ratio and proportion, we found the cost of one particular weight of cheese. Now, with the formula, we can substitute anything we like for the weight and find the cost. Perhaps all this seems a little more complicated than the simple proportion we had earlier, but now it's much easier to change the weight. You want 12 kilograms of the same cheese? $20. The formula gives it to us in a flash, and the same for any other weight of the same cheese. This is a useful technique, so let's be clear about how we got to where we are right now. Here are the steps we used. First to find the constant, and then to solve the problem. That's all. Good news. And here's the better news. We can use the same process to solve more complicated problems. For example, say the amount of gas your car consumes is proportional not to your speed, but to the square of your speed. It takes 6 gallons to get you to the beach at 45 miles per hour, but you choose to drive 55. How many gallons? The first sentence gives the key to the formula. This time we need s squared for the square of the speed. And K is the constant of proportion just as it was before. Will the equation handle our problem for us? Sure it will. You can do it by yourself. First step, find the value of K. How? By using the figures given in the problem itself. That will give you your formula. Then plug in the new speed, 55 miles per hour, into the formula and find out how many gallons of gas it will take you to get to the beach. First, the value of K. If the gas is 6 gallons when the speed is 45, then G equals K times 45 squared. Which tells us that K equals 6 over 45 squared. And you can turn that into a decimal with a calculator if you want to. Leaving it as a fraction, we now have our formula for the whole relationship between your gas consumption and your speed, which means that we can plug in the new speed, 55, and find almost instantly that you use a lot more gas at 55 than you did at 45. What else can we do to complicate things? Well, sometimes you see the word inversely in a proportion. That means that as x gets bigger, y gets smaller. How do we show that in the equation? Exactly the way you see it here, by using a fraction with a numerator of 1. Check it out, it works fine. Or you might see several variables together on one side, with or without the word jointly. In that case, you have to multiply all of them together, still with a constant k, just like before. Here's how that looks in practice. We have two spaceships out there. We know that the force of gravity between two spacecraft varies jointly with their masses. Here the force is 60 units. Question: how much mass does the second spaceship have to jettison to reduce the force to 50 units? First, we translate to get our formula. We have a constant and a mass for each spacecraft. The force equals the constant times the first mass times the second mass. Next, what is that constant? We substitute the numbers we're given in the problem. That lets us find out that the value of K is 3/10. And that gives us our real formula, the one we can work with to solve the problem. Now we want to reduce the force to 50 by keeping the first spacecraft the same as before and changing the mass of the second one. So what we have to do is substitute the numbers and get an equation for M2. So the second spacecraft needs to reduce its mass from 20 tons to 16 2/3 tons. It needs to throw out 3 1/3 tons. Finding the answer with the formula? That's easy. Throwing out 3 1/3 tons into space? That's not so easy, but it's correct. With this technique, we can solve lots of problems about light, sound, magnetism, and gravity. They all share the same law, where one variable is inversely proportional to the square of the other. Another problem. This one's about your favorite rock band and why you're going deaf. If sound varies inversely with the square of the distance, where can you sit to make things a little quieter? Say a discrete 20 decibels. Try this one yourself. Translate to get an equation with K in it. Substitute the 2 and 100 and solve for K. Then substitute 20 into the new formula. I start by translating the description into a law that reflects the inverse relationship with a fraction, and the square of the distance as d squared in the denominator. Then I want the constant, so I take the values we were given, substitute for s and d, and solve for k. K turns out to be 400. So I put that into the equation, and there we have it, the real formula connecting the sound and distance. Then I want to find out exactly where the sound is 20 decibels. So I substitute the 20 into my formula for S and solve for D. So there's where I want to sit to give my eardrums a rest at a mere 20 dB. You'll find lots of applications that can be solved using this sort of technique. You'll find some of them in your textbook. Be sure to take a look, and good luck.